Hi kids, we'll be going with this magnetism revision. So I'll be going in step by step. So the first question was like, if there is a charge which is at rest and there is uniform magnetic field in this direction, charge is at rest, then what will happen to this motion in future? So magnetic force will be how much? Q into V bar cross B bar, but V is 0, so magnetic force will be 0. So if magnetic force is 0, acceleration will be 0. If acceleration is 0, final velocity will be same as initial velocity, which is 0, that is this will be at rest forever. Now going to the next question, if there is a particle whose velocity is along the direction of that magnetic field, what will happen to its motion? So Q into V bar cross B bar. V bar and B bar are along the same direction, so V bar cross B bar will become 0. So that is the force on this one is 0. If force is 0, acceleration is 0. The meaning is final velocity will be same as initial velocity, or it will be moving with the constant velocity along this direction. Now similarly, if V bar is anti-parallel to B bar, so if V bar is in this direction, B bar is in this direction, then what will happen? The force will become 0. Q into V bar cross B bar is 0. So it will be keeping on moving with that uniform velocity. Now if there is magnetic field along z axis, now I have taken x, y and z, I cap cross j cap is k cap, so that must be matching. Okay, so if magnetic field is along z axis and velocity is in the plane of x and z, so I am calling its component along x axis as ux, its component along z axis as uz. So what is the initial velocity? Initial velocity is, I am observing this from ground frame, right? So velocity along x axis is ux, along y axis is nothing, initial velocity along z axis is uz k cap. Now what about magnetic field? Magnetic field is along only z axis, that is magnetic field is 0 I cap plus 0 j cap plus b k cap. Now at any moment, let me say the velocity is v bar equal to dx by dt I cap plus dy by dt j cap plus dz by dt k cap, right? So that dx by dt I am writing it as x dot. This mean x differentiation with respect to time, right? Y dash, z dash, right? Now I'll be trying to find what is the force at any instant. If I want to find force at any instant, what I need to do? Q into V bar cross B bar. So I am trying to find V bar cross B bar. V bar I am going to take it from here, and B bar I am going to take it from here, and I am going to find the cross product. When I find the cross product, it is turning out to be something like this. What does this y dash represent? Dy by dt. What does this x dash represent? Dx by dt. Now you can see here, this is 0. So V bar cross B bar is 0 along k cap. So Q into V bar cross B bar is also 0 along k cap. The meaning is there is no force along k cap direction at any moment. So what I am doing is, now I got V bar cross B bar is this much. From here, if I want to find force, what I need to do? I need to multiply with Q. Q into V bar cross B bar will give me force. So if I divide with mass, I will be getting acceleration. So I will be multiplying with Q and dividing with m, so that I will get acceleration. So what is the acceleration along x axis? It is Q by m into y dash into b. What is acceleration along y axis? Q by m into minus x dash into b. Now what about acceleration along z axis? It is 0. If acceleration along z axis is 0, then from there I can say velocity along z axis is constant, which is uz. So distance traveled along z axis or z coordinate will be depending on time in this manner, right? uz into t. So motion along z axis is quite simple. Now we will look at motion along x axis or along y axis, what is happening. Now if you see here, x double dash is dependent on y dash, y double dash is dependent on x dash. So I can't, here there are three variables, y, x and t, so I can't integrate as such. So what I am going to do is, I am going to differentiate this. If I differentiate this, I will be getting y triple dash equal to minus qb by m into x double dash I know from here, so I am going to substitute x double dash from here. So from here what I will be getting, finally I will be getting y triple dash equal to minus qb by m whole square into y dash, right? If you look at this one like some function x, if this is x, then this is going to be x double dash, right? Because this is y dash, this is y triple dash. So if this is x, then this is going to be x double dash. Now this must look like SHM equation. Where that x variable is y dash. So I can say this looks like SHM equation. So y triple dash equal to minus omega square y dash. So if I take y dash as my variable, so y dash will be performing SHM, right? Y dash double dash. y dash double dash equal to minus omega. So this must be SHM. So what must be the, so this must be SHM. Now what is omega? I have said like this is kind of omega. So what is the omega? I assumed QB by M. So this will be performing SHM. So this is the equation we got. So this will be performing SHM. So the general solution of SHM will be P sin omega t plus Q cos omega t. P sin omega t plus Q cos omega t. General solution of this one is P sin omega t plus Q cos omega t. Now differentiation of this one will give me P omega cos omega t minus Q omega sin omega t. Now there are two variables P and Q, so I need to find what are their values. So I am going with the initial condition. At t equal to 0, what is the velocity along y-axis? At t equal to 0, what is the velocity along y-axis? Now if you see here, at t equal to 0, what is the velocity along y-axis? 0. So at t equal to 0, velocity along y-axis is 0. So t equal to 0, when you substitute, this term will become 0, this term will become q into 1, right? So t equal to 0, this is 0, now this is 0, this is going to become q. From here I can conclude q is 0. At t equal to 0, what is the acceleration along y-axis? What is the acceleration along y-axis? Now if you look here, at t equal to 0, what is the acceleration along y-axis? I can find it easily like u bar cross b bar, u bar cross b bar, right? U bar cross b bar by q into u bar cross b bar by m. That is in negative y-axis, negative y-axis. So acceleration along y-axis is in negative direction, and how much it is? Minus q into ux into b by m. This is the initial acceleration along y-axis. So t equal to 0, when you keep it here, it will become p into omega, this one will become 0. So from here, and I know what is the value of omega I assumed, right? So qb by m. So I will be bringing it back here. I will be substituting omega as qb by m. From here I will be getting p equal to minus ux. So I assumed solution will be of this form. I found value of q is 0, value of p is minus ux. So I know the solution of y dash. So I know the solution of y dash, how much it is. Instead of p, I need to substitute minus u. Instead of q, I need to substitute 0. So this term is going to be 0. So this term is going to become minus ux into sin omega t. Minus ux into sin omega t. Now if I integrate it, what I will be getting? Integration of this one is going to become plus ux cos omega t by omega. So plus some constant will be coming. Now this constant, I know it has to be ux by omega. Now how I got it is, y coordinate initially is 0. So the meaning is, when I substitute t equal to 0, this total term has to become 0. So this one will become ux by omega. So the remaining constant must be minus ux by omega. So from here what I can get? I can get y coordinate is ux by omega into cos omega t minus 1. That ux by omega, what I am doing? I am assuming it as some r. Ux by omega, I am assuming it as some r. Okay, so r will turn out to be how much? M into ux by qb anyway. Now I got y, but I need x also. So what I will be doing? I will take this equation. And try to solve it. So x equal to qb by m. X equal to qb by m into y dash, which is omega into y dash. So x equal to omega into y dash. Now y dash, what I did? I substituted y dash from here, and I got some result. Now from here what I will be doing? I will be integrating. So I will be getting x dash equal to integration of this one is omega r cos omega t plus some constant. That constant is going to be 0. How? I know at t equal to 0, x is omega into, x dash is omega into r, because omega into r, if you multiply, what you will be getting? Omega into r is ux, omega into r is ux. So this is ux cos omega t. So from there I can get the constant value as 0. So if I integrate this one further, I will be getting x equal to r sin omega t, because that constant is going to be 0. So anyway, the method is not so important, but what is the results I got? X equal to r sin omega t, y equal to r cos omega t minus r. So if I modify this, like if I want to eliminate time, r sin, r cos, so I need to square them and add them. So what I will be getting? X square plus y plus r whole square equal to r square. So what does this represent? This represents a circle whose center coordinates are 0, minus r. So basically 0, minus r, in the sense it will be performing, yeah, if this is x-axis, if this is x, this is y, and this is z, then it will be performing circular motion like this, circular motion like this with radius r. But what is r? R is m into ux by qb, m into ux by qb, that is ux is this one, ux is this one. So if you forget uz, if there is only ux, then what will happen? Ux cross b, so it will be performing circular motion of radius m into ux by qb, m into ux by qb. So how the equation, final equation is looking? The final equation is looking, if I look at only x coordinate and y coordinate motion, it looks like a circular motion which is depending on only ux. But what is happening to y axis motion? Y axis motion is uniform velocity motion. So sorry, not y axis, it is z axis. So z axis motion is uniform velocity motion. So if you don't worry about z axis, what happened? It is performing circular motion in xy plane. It is performing circular motion in xy plane. But if you worry about z axis, in z axis it is constantly moving with it is having uniform velocity. So it will be performing circular motion, at the same time it will be moving forward, so which will be helical motion, right? Anyway, you people must have taken it for granted. So I mean, this is how generally we do it. We try to give the work to maths, and whatever results we will be getting, we will be trying to understand it in a simpler way so that we can use them further. Now this is how we do it generally. So if initial velocity of the particle is in this direction, if magnetic field is into, and if the charge is positive charge, so the force will be q into u bar cross b bar. Yeah, I mean, if there is no z component in this question, the final result will turn out to be only two-dimensional, which is circle. That is, if the velocity and magnetic field are perpendicular, then it will be performing circular motion. So I can prove that it will be performing helical motion when velocity makes some angle with magnetic field, and I can prove it will be only circular motion when velocity is perpendicular to magnetic field. Now how we will be understanding the results is this way. So if there is a charged particle going, initial velocity is this direction, magnetic field is into, if the charge is positive charge, then q into u bar cross b bar, that will be the force which will be responsible for the circular motion. So q into u bar cross b bar will be giving the required centripetal force. From there you will be getting radius, from there you will be getting time period, and note that the time period doesn't depend on the speed of the particle. If it is negative charge, then it is q into u bar cross b bar, but q is negative charge, so it is going to be this direction, so it will be performing circular motion like this. Now note that it doesn't depend on velocity, right? Now the same thing, if velocity is making some angle with magnetic field, we will be resolving the velocity along the magnetic field and perpendicular to the magnetic field, like we did in the previous question. Now what we understood from previous question from math, because of this velocity, if you take this velocity, because of this velocity v bar cross b bar, the force is in this direction if it is positive charge. So what will happen, it will be performing circular motion like this, but because of this velocity it will be moving forward, so it will be performing helical motion. Now if there is other question which says electric field is along y axis and magnetic field is along z axis, and a particle is placed here right now at rest, placed here. Now what will be the kind of motion this particle will be following? Now we are observing from ground frame, from this frame where this particle is at rest. Okay, so what we are going to do, we are going to follow the same math. So electric field is along y axis given, magnetic field is along z axis given, initial velocity is 0 given, initial coordinates are 0 given, and so at any time velocity, if I take it as dx by dt I cap plus dy by dt j cap plus dz by dt k cap, so I have to find the net force. Net force is q into v bar cross b bar plus q into e bar. So I am going to find v bar cross b bar, I am going to take v bar, I am going to take b bar. So when I find v bar cross b bar, I will be getting something like this. Now I need to find the net force. Net force is q into e bar plus q into v bar cross b bar. E bar is already known here, so q into e bar will be playing role only in j cap, and plus q into v bar cross b bar. So multiply this one with q and just add it here. So this is the net force. If this is the net force, if you divide with mass, you will be getting acceleration. So if you divide this with mass, you will be getting this much. If you divide this with mass, you will be getting this much. If you divide this one with mass, anyway it will be 0 only. So acceleration along z axis is 0, y axis is this much, x axis is this much. Now let us analyze about x axis. Acceleration along z axis is 0, so velocity along z axis will be constant, which is 0 initially. So there won't be any motion along z axis. So that is going to be much simpler. So now there won't be any motion along z axis, so the motion entirely will happen in this plane. That's what we understood. So the motion is going to happen in this plane, and we will see how it is going to happen. Now again, this is x, this is y, this is y, this is x, so it is not so easy to integrate, so we will be going to follow the same method. We will try to differentiate one thing, so that if x double dash comes, I can substitute it from here. So I am going to take those two terms. I am going to take x double dash, y double dash, what we got, I am going to differentiate it. So then this is qe by m is constant, so the next one will turn out to be qb by m into minus x double dash, x double dash. But what is x double dash? I can substitute it from here, so I will be getting something like this. Again, I am assuming this as omega, so then I will be getting of this form. If it is of this form, then again I will be getting the general solution as HHM, so which will be p sin omega t plus q cos omega t. Now if I differentiate it further, I will be getting acceleration is p omega cos omega t minus q omega sin omega t. So at t equal to 0, what is the velocity along y axis? Velocity, initial velocity was 0, so at t equal to 0, this is 0. When you substitute t equal to 0, this one will become 0. When you substitute t equal to 0, this will become q. So 0 equal to 0 plus q. From there I can say q is 0. Now what about acceleration? What about initial acceleration along y axis? Initial acceleration along y axis. Initial acceleration along, what is the initial force along y axis? Which is q into e. So what is the initial acceleration along y axis? qe by m. So initial acceleration along y axis is qe by m. At t equal to 0, this is going to be qe by m, this is going to be p omega, this is going to be 0. So from here I will be getting, omega value is qb by m. When I substitute, I will be getting p value as e by b and q value as 0. So I assumed this will be the general solution. I got the value of p, I got the value of q. So when I substitute it back, q is 0 and p is e by b, I will be getting velocity along y axis as this much. Velocity of y axis as this much. Now what I am doing is I am calling this one as v0. I am calling this e by b as v0. I am calling that e by b as v0 for simplicity. So from here I will be getting y. If I integrate it, I will be getting integration of this one is minus v0 by omega into cos omega t plus some constant. That constant I can easily prove it is v0 by omega, because at t equal to 0, this y coordinate is 0. So I will be getting, now from here v0 by omega, I am assuming it as r, so that I can write it much easily. So y equal to r into 1 minus cos omega t. Now I got y, I need to find x also. So what is x double dash? X double dash is qb by m, which is omega into y dash. Omega into y dash. So x double dash equal to omega into y dash. What is y dash from here? This is y. If I differentiate this, I will be getting y dash. I can substitute it. Now I can integrate it. Again, that constant I can easily prove it is omega r. Now again I will be integrating this. This integration is going to be this one. This integration is going to be this one. There will be some constant. I can prove that constant is 0 by substituting what is the value of x coordinate at t equal to 0. 0 equal to 0 plus k2. So k2 is going to be 0. So x coordinate is going to be this much. So what I got, x coordinate is going to be this much, y coordinate is going to be this much, and we already understood there is no motion along z axis, right? So if I want to eliminate time, that is if I want to find how the trajectory looks like, I have to eliminate time. So what I am going to do, kind of r sin omega t, r cos omega t, I will be squaring it and adding it. So I will be getting this much, x minus r omega t plus y minus r whole square equal to r square. Now this is equation of cycloid, which is cycloid. Now I'll show what does it mean by cycloid. Now what does this say? This looks like circular motion. This looks like circular motion where y coordinate of center is r. This is a circular motion whose center coordinates are r omega t comma r. That is x coordinate center. Okay, x coordinate of center is varying with time, but y coordinate of center is not varying with time. Now that looks like this. The cycloid looks like this. Now if you see here, this is the center and its y coordinate is always r. Y coordinate is always r. But what about x coordinate? X coordinate is moving forward. Now at any time, what will be the x coordinate? It is v into t. But under pure rolling, v equal to r omega. That is r omega into t. So this motion. Now if you put some dot at some point and if you trace that particular point, whatever motion is happening, this is called as cycloid motion. So this is the kind of motion what we will be getting in that particular case. Right, so you can see like it will be performing circular motion and it will be moving forward. Now if you if you neglect this one, then it's like it is performing circular motion with coordinates 0 comma r. But if you look at this one, that x coordinate is moving forward. So you can visualize it like motion about center of mass and motion of center of mass, right? So after, at what distance from here? At what distance from here it is turning back? It is r plus r 2r, r plus r 2r. But what is our r? Our r is okay. So I think you can get everything from there. Yeah, when you do this, you know V naught, you know what we assumed about omega. When you substitute everything, then you will be getting what is the radius also easily, right? So now going to the next part. Yeah, why I have done this one is like I have left everything to math. Only after getting the result I tried to understand what is the result. I didn't assume something like it is going to be circular or helix or something, because I don't know what is going to happen. Now these are some very regular cases what we will be discussing. If there is some case other than this coming into picture in your exam, I think we have to depend on math. We have to depend on math. Only then we have to analyze the result. Now going to the next part, it's like suppose, okay, we know the net force on the particle will be given by q into e bar plus q into v bar cross p bar. That is, if I take example like if I am observing from some ground frame and if the particle is moving with a velocity v bar, where electric field is e bar and magnetic field is v bar, then the net force on this one will be q into e bar plus q into v bar cross v bar. So that's the net force. But if I observe the same thing from a frame which is moving with a velocity v, if I observe the same thing from a frame which is moving with a velocity v, what I will be feeling? I will be feeling this is at rest. If I feel this is at rest, what will be the force exerted because of this magnetic field? 0, because q into v bar cross v bar, it is velocity is 0. So magnetic field won't be exerting any force for me. What about force exerted by this electric field? It is going to be q into e bar. So the net force is going to be only q into e bar, which is less than this. But we know, I mean, yeah, it is true that these two frames are equivalent to each other. There is no both are moving with constant velocities, right? So both are inertial frames. So in inertial frames, net force has to remain same. So there is something wrong here. Now what is that thing wrong is, if I try to understand, the net force has to be same as initial case. So the net force has to be this much, q into e bar plus v bar cross v bar. The net force has to be this much. And it can't be magnetic field because it is at rest. So it is going to be electric field. So, or else the other way of saying it is, in this new case, the electric field won't be same as earlier one, but there will be some kind of new electric field coming into picture. So the net electric field is going to be e bar plus v bar cross v bar. So when you shift your frames, electric fields and magnetic fields will be changing. Now that's the point I am going to stress on here. So be aware, you must not shift frames just like that. I mean, it's always better don't shift frames in electricity and magnetism, right? So how they are going to change is, we are going to look at the same question where electric field is along this direction, magnetic field is along this direction, and particle is at rest. Now, okay, generally when v naught is much less than c, where c is speed of light, so then new electric field is going to be e bar plus v bar cross v bar, which I have shown here. New electric field will be e bar plus v bar cross v bar, where v bar is our frame's speed. So e bar, new electric field is going to be this much, but it's not so easy to show what is new magnetic field, so you can just take it for granted. New magnetic field is going to be old magnetic field minus v bar cross e bar by c square. So that is, if I start observing this thing from a frame which is moving with the speed v naught, if I start observing this one from a frame which is moving with speed v naught, what I will be feeling? I will be feeling the new electric field is old electric field plus v bar cross v naught bar cross v bar. So old electric field is E. Now v naught bar cross v bar, v naught bar is in this direction, v naught bar cross v bar is going to be in this direction. So v naught into b, this term is going to be this much. Now what about this one, b bar minus v naught bar cross e bar? Now v naught bar V naught bar cross E bar is going to be this direction, but it is minus, so it is going to be this direction. So this is this term. So I need to add these two, or yeah, they are in opposite direction, so I can subtract. Then I will be getting net electric field, then I will be getting net magnetic field in the new frame. In the new frame, what is the net electric field? E naught minus V naught into B. What is the net magnetic field? B minus V naught into E by C square. But what I am going to do is, I am going to choose my V naught wisely. So that net electric field will become 0. That is E equal to V naught B I will be taking. If E equal to V naught B, then V naught equal to E by B. So I am choosing my speed such a way that net electric field is going to become 0. Then what will happen to net magnetic field when I substitute V naught equal to E by B, or E equal to B into V naught. If I substitute E equal to B into V naught here, I will be getting B into V naught square by C square. But what we did in the first place, we are going to do when V naught is much less than C itself. So this term is going to be very small. So I can neglect. I can say almost the net magnetic field is B only. So when I start observing from a frame which is moving with the speed E by B, what I will be feeling? I will be feeling net electric field is 0, but magnetic field is almost B. So now from this frame, it is going to be quite easy for me, because from this frame what I understood, there is only magnetic field along this direction, and particle, I will be feeling particle will be having a velocity V naught in this direction, because from ground frame it is at rest. So when I start observing from this frame, I will be feeling the particle is having extra velocity this direction, right? So if the particle is having velocity this direction and magnetic field is this direction, particle velocity is this direction, magnetic field is this direction, so what kind of path it will be following? V bar cross B bar forces towards this way, so it will be performing circular motion. So from this frame, I will be feeling it is performing circular motion. So now what will happen if I shift my frame? Like this entire thing will be moving forward with a uniform speed V naught. So I will be feeling it's a circular motion when I am observing from a frame V naught. So when I shift my frame to ground, then I will be feeling this entire circle is moving forward with a speed V naught. So then I will be getting again that kind of pure rotation kind of thing and cycloid kind of thing, right? So everything from here you can get everything. So from this frame you will be feeling it is circle, but when you move on to the other frame, you will be getting cycloid, where that center will be moving with the speed V naught into T forward. So the same result we got in the other way, but this is going to be much simpler. Like previous one, if you have seen, I have done integration and stuff and SHM and equations and stuff, but this is going to be quite simple, right? So when we observe from a frame which is moving with V naught, we found it is circle. So when I shift my frame to ground, that center will be moving with speed E by B. Now overall, when you look from ground frame, it will be performing cycloid motion. Obviously both ways must give you the same result. Now this is the same question, but in scalar form. Maybe if you want, you can try it without knowing the equation of trajectory. Still, like if they ask you something, you can do it by this way. You can refer to it. Now the next question is, if there is electron which is performing circular motion, then equivalent current will be Q by, or else how much charge will be passing through any particular point in unit time, that is Q by T, which is 2 pi by omega. So equivalent current will be this much. So what will be the magnetic field produced by the electron at the center? If electron is going this way, then we will be saying like current is in the opposite direction, right? So if current is in this direction, then the magnetic field will be into, magnetic field will be into, or magnetic moment will be into, magnetic moment also will be into. So I into area in this direction. So this is the magnetic moment. I can substitute it from here, and I cancel, I will be getting this much, but it is into, magnetic moment is into. Now what about angular momentum? Angular momentum is I into omega, or mr square into omega, but what about the direction? It is this way, So from here I will be getting this relation, magnetic moment equal to minus q by m times of L bar, because it is electron, because it is negative charge, we got this direction as this way. If electron is going this way, current direction is going to be this way. If electron is going to be this way, current direction is going to be this way. So that is the reason we are getting the direction as into here but out here. But what happens if it is a positive charge? Then magnetic moment and angular momentum will be in the same direction. So you will be getting mu bar equal to q by m into L bar. Anyway, magnitude wise the ratio will be equal to q by 2m. Now how we got this result? When we can visualize the charge or some particle, if some particle having a charge E and mass m, then we are getting this relation. So if there is any situation where you can visualize that situation, like some particle will be carrying charge q and mass m, like if they say like uniformly distributed mass and charge, so you can visualize like each particle having some specific amount of charge and specific amount of mass. So in that particular case where you can visualize any situation like charged particles, like same mass and same charge, then you will be getting this result. I mean this result will be valid there. So most of the places you will be getting this result. So the next question is, if there is a small current carrying wire placed in a uniform magnetic field or in a magnetic field, that small wire will be almost, I mean even if it is non-uniform, still in that small area wherever the element is placed, the magnetic field will be uniform. So this is the force on the element. Now if I want to find the force on the loop, I have to integrate for loop. Now I is going to be a constant because we will be talking about steady state currents only. So now from here to here, what I am doing is, if magnetic field is uniform, what I can do is I can say this integration is going to be same as this integration. So now what about integration of closed loop? What will happen if you add small displacements? Like if there is a closed loop, this is like adding small displacements. If you add small displacement, then resultant will be final displacement. For a closed loop, you will be coming back to the same point, so displacement is going to be 0. So integral dl bar for a closed loop is going to be 0. So the result is going to be 0. The other way of saying it is, if you place a closed current carrying loop in a uniform magnetic field, if you place a closed current carrying loop in a uniform magnetic field, then the net force on it is going to be 0. Now based on that, if someone asks you like to find the force on this current carrying element, yeah, there must be some closed path for the current to flow, but I am not bothered about that. I am bothered about what is the force acting on only this part. Then what I am going to do, I am going to add some current I and add some current I in this direction. So effectively I am adding 0 current. So this situation is same as this situation. I am seeing this 0 current as summation of this current and this current. Now why I am going to do that is because then I can see this entire thing, this black color thing and this blue color thing as one closed loop. So what will happen if I place a closed loop in a uniform magnetic field? The force on this one is going to be 0. The force on this closed loop is going to be 0. So I need to find only force on this one. So effectively force on this one is going to be finding force on only this one. Now what is this? This is nothing but equivalent to this one. So generally you will be saying like effective length. You can join initial point to the final point and you can say like directly current is going from here to here. And if you find the force on this one, which will be same as force on this one. Now what is the step-by-step method? This can be the easiest way of easiest way of going in step by step. I personally feel, make a closed loop. On a closed loop force is 0, so whatever force, net force, it has to be only on the remaining part. Now you can try this question by yourself. Now here if you see, this side there is uniform magnetic field. Uniform in the sense direction also must be same, right? So B into, but this side there is B out. So this entire thing is uniform, this entire thing is uniform, but these two are not equal. So what we need to do is, if we want to find the net force, we need to choose our elements. If we want to find the net force, we need to choose our elements such that magnetic field is uniform. So I am going to choose this one plus this one because the entire magnetic field is B into. Now again I am going to choose this one also, so that the magnetic field is into on for this element. I am going to choose this element so that the magnetic field is out, uniform. I am going to choose this element so that the magnetic field is out and uniform. So instead of this thing, what I can do, I can replace with a wire like this, and instead of this thing I can replace with a wire like this. Instead of this thing I can replace a wire like this, but for that wire you have to find force because of this one. Now similarly, instead of this one I can replace a wire like this. Now force on this wire will be because of this magnetic field. So when you find all those 4 forces and when you add them, you will be getting the resultant. Now what we have seen here, when you keep a closed current carrying loop in a uniform magnetic field, then the net force is going to be 0. But what we know something like torque is m bar cross b bar, where m bar is magnetic moment of the current carrying loop, right? But the torque is about which axis? We never mentioned like the torque is about which axis. But when you see here, this I have taken in rotation. You can refer back rotation if you don't get it. It says like if the summation of forces is 0, then when you calculate torque about point P, that will be equal to torque about point O. When you calculate torque because of those forces whose sum is 0. Now in this particular case, net force because of net magnetic force is 0. That is, when you add all small magnetic forces, net is going to be 0. Net is going to be 0. Then no matter about which point you calculate torque, it is going to be same and is equal to m bar cross b bar. M bar cross b bar. So m bar cross b bar is about any point. So if the net force is 0, then the torque because of those forces is going to be independent of your point of reference. So the next one is if there is a current carrying wire. So if you want to find the magnetic field here, I think you must have learnt it in the class. So it will turn out to be something like this. But the easy way of remembering it is mu naught I by 2r into sine cube theta. That you can see when you get to the center, that theta will become pi by 2. So then it has to become mu naught I by 2r, right? So now what happens if x is much greater than r? You will be getting something like this, where I into pi r square, you can visualize it like magnetic moment. When you visualize it like magnetic moment, you will be getting mu naught by 4 pi into 2 into magnetic moment by x cube, which is exactly similar to mu naught, that k into 2p by r cube form in electric dipole, right? So what does this say? This say only when x is much greater than r. The meaning is only for far away points, closed loops will behave like dipoles. Only for far away points. Now this is the example where you can use that sine cube theta to get the answer quickly. Now there is other question. The question says like, if there is a current carrying loop like this and if the magnetic field at the center is B naught J cap. Now direction you can get by symmetry, but what about the magnitude? They said it is B naught J cap. Now because of this current carrying closed loop, what will be the magnetic field? That's what they are going to ask. So what we are going to do? Now they have given only currents this way. So but what I am going to do, I am going to make this loop first. Now if I want to make this loop, what I need to do? I need to add some current in this direction. So if I am adding, I must subtract also, so that I must not change the situation. So I am going to add some current like this, subtract some current like this. Now similarly, I am going to add some current like this, subtract some current like this. Now similarly, now I can see a loop here. Okay. Now if I want to make this one a loop, I have got this current, but I didn't get this current. So I am going to add some current like this, subtract some current like this. So I can see a loop here also. I can see a loop here also. So there are three colored loops. Now because of this colored loop, because of the red colored loop, it is magnetic field is B naught into I cap. Because of this blue colored loop, it is B naught into minus I cap. Now what? Because of this green colored loop, it is B naught into K cap. So the resultant will be B naught into I cap plus minus I cap plus J cap plus K cap. Now the next question goes like, if there is a current carrying cylindrical wire. So this is a cylindrical wire and current is, let me say, flowing into the wire. So this is the cylindrical wire, current is flowing into the cylindrical wire, solid, right? So current density will be I by pi into capital R square. Now I'll be using Ampere's law, integral B bar dot dl bar equal to mu naught times of current enclosed. If I want to find the field inside at a distance r, how I will be going to find? So I will be using Ampere's law. Now again by symmetry I can say, if the current is going into, magnetic field will be clockwise direction. So magnetic field at this particular point will be in this direction. So anyway, at magnetic field at every point has to be same by symmetry. So and it is along the direction of dl. I am going to take this direction. So dot product is going to be B into dl. So how I got this one? By symmetry, I know magnetic field has to exist only tangentially. So from here to here I am getting. Now I can take B out of integration, because by symmetry I can say magnetic field magnitude has to be same at every point. Now what is integral dl? Integral dl is 2 pi r. Now what about right hand side? Current enclosed. Current enclosed is current density times this area, current density times that area. Current density is I by, okay, anyway, put it in current density form because it is going to be easy. So when you do that, you will be getting finally magnetic field is mu naught by 2 into j into r. But if you want to put it in vector form, r bar is this direction, j bar is this direction, r bar, j bar, but magnetic field is this direction. So anyway, r bar is this direction, j bar is this direction, magnetic field is in the downward direction. Now how I can get it? If I take r bar cross j bar, it is going to be this direction. If I take j bar cross r bar, it is going to be this direction. So if I want to get this direction, then it is j bar cross r bar. So magnetic field, if I want to put it in vector form, it will turn out to be mu naught by 2 into j bar cross r bar. Now once you see it is in linear form, whatever we did in electrostatics, we will be doing it again here. It is cavity. If there is a current carrying cylindrical wire and there is a cavity, and if you know this position vector is L bar, what will be the magnetic field at any point inside the cavity? So what I will be doing, this question is equivalent to finding field because of this entire cylinder and finding field because of the small cylinder and subtracting them. Now because of this cylinder, magnetic field is mu naught by 2 into j bar cross r1 bar. Field because of this cylinder is going to be mu naught by 2 into j bar cross r2 bar. Now if I subtract them, then I will be getting r1 bar minus r2 bar. R1 bar minus R2 bar. R1 bar minus R2 bar is going to be L bar. So which is going to be again a good result, exactly like electrostatics. Now the next question goes like, a long straight wire carries a current I into the plane of the figure. AB is a straight line. Okay, whatever it is. So there is a current carrying wire here. So you need to find integral B bar dot dl bar along this line. Now similarly, the next question is, you want to find integral B bar dot dl bar for this one. So what I am going to do is, I am going to take the first figure where you have to find integral B bar dot dl bar for this wire. Now what I am going to do is, I am going to draw a circle of this radius OA, and I am going to draw a circle of radius this OB, and I am going to extend this line. Now I am going to take this loop. Now why I am going to take this loop is, if the current carrying wire is like this, then the magnetic field will be concentric circles. So integral B bar dot dl bar will be 0 for this line. Concentric circles, they will be perpendicular. So integral B bar dot dl bar will be 0. Now for this loop, B bar is this way, dl bar is this way. So integral B bar dot dl bar is going to be negative, and how much it is? It is going to be theta by 2 pi times of mu naught I magnitude wise. That you can calculate easily, because you know the magnetic field here will be mu naught I by 2 pi r, and into this length is going to be r into theta. That you can calculate easily. But what I know for this loop there is no current enclosure, so the net B bar dot dl bar must be equal to mu naught times of current enclosure, which is 0. So this is already 0. This is minus mu naught I into theta by 2 pi. So this has to be plus mu naught I into theta by 2 pi. Now radial elements will help you, because integral B bar dot dl bar will turn out to be 0 for radial elements. Now you can go with the same logic for the next one. If you want to find integral B bar dot dl bar for this one, again I will be taking a closed loop like this. Along this one, integral B bar dot dl bar is 0. For this one we already got something. So for this one also it has to be the same thing, because integral B bar dot dl bar for this closed loop equal to mu naught times of current enclosed, which is going to be 0. Now the next one, if there is a infinite current carrying sheet, it's like a sheet. If there is a sheet like this and current is coming out, if you want to find the field here at a distance x, how much is going to be that field, where k is given as current per unit length. If you take unit length here, current in that length is k. Now what you can do, you can take Ampere and loop, and you can easily see magnetic field will be uniform in this direction. So integral B bar dot dl for this one is 0, this one is 0. For this one it is going to be B in, if I take length L, so it will going to be simple B into L. So integral B bar dot dl bar for this closed loop is going to be 2 times of B into L, that equal to mu naught times of current enclosure. 2 times of B into L equal to mu naught times of current enclosure. Current per unit length is K, so current for this much length is K into L. So magnetic field is mu naught K by 2, where K is current per unit length, and which doesn't depend on distance. Right, now why I am going to do this is, because in electrostatics we have done something like this. You can refer electrostatics if you didn't refer, and we found pressure, and we have seen like how we will be doing for a spherical uniformly charged sphere. Now we are going to do the same thing. We are going to take a sheet whose current is going in this direction for a sheet, and magnetic field on this side is B1 making angle theta 1, magnetic field on this side is B2 making angle theta 2. Now what about this B1 and B2? This is the resultant of external magnetic field and field by itself. Now what I am going to do, I am going to resolve into horizontal component, vertical component, horizontal component, vertical component. This is not so important, but this horizontal component consists of, okay, so this horizontal, okay, this magnetic field consists of its own magnetic field plus external magnetic field. Now let me say if the current is going in this direction, what will be the if the current is going in this direction, what will be the direction of magnetic field here? Direction of magnetic field here will be L bar cross R bar, L bar cross R bar, which is going to be this direction. Magnetic field direction here will be L bar cross R bar, which is going to be this direction, but value we got it already, mu naught K by 2. So magnetic field, because of this current carrying element, current carrying sheet, is going to be mu naught K by 2, mu naught K by 2. Now external magnetic field, I am taking like Bx, By, By, Bx. Okay, so the summation of this external plus this this magnetic field is going to be this much, or this much, or this side the external magnetic field plus magnetic field because of this current elements is going to be this much or this much. So basically this is the result of external magnetic field plus its own magnetic field. This is the result of external magnetic field plus its own magnetic field. Now what we need to do, we need to find pressure. Pressure means we need to find what is the force acting on in this direction, and we need to divide with the area. Now this magnetic field is in this direction. This current element, if I take, it will be in this direction. So L bar cross B bar, that is going to be along this direction. But this force is not required for me because it is not going to give pressure. If I want to find pressure force, that must be because of this magnetic field. That is, if the current carrying wire is into magnetic field is this way, so then it is L bar cross B bar. So that is the force which is needed for me. So if I take some current carrying element and if I find the force because of this Vy, that is going to give me the force in this direction. If I divide with area, then I will be getting pressure. So anyway, if I add these two, what I will be getting? Mu naught K by 2, mu naught K by 2 will be getting cancelled. So basically I will be getting 2 times of external electric field. So B1 bar, this entire thing, okay, this entire thing, B1 bar plus B2 bar will give me 2 times of external magnetic field, or B1 bar plus B2 bar by 2 will give me one time of external magnetic field. Now similarly, I am going to see like what will happen if I subtract B2 bar minus B1 bar. If I subtract these two, what I will be getting? I will be getting mu naught K by 2, mu naught K by 2. Totally it is mu naught into K in this direction, mu naught into K minus J cap. But what I need to find force on unit area, force on unit area. Now what is the current in unit length? If I take unit length here, what is the current in this? Current in this is K. Now I am going to take unit length in this direction also, So this length is going to be 1 unit again. So what is the current? Current is K. And what is the length of the element? Length of the element is 1. So I into L is 1 into By. So this is going to be the force on unit area, Now how I can write this one? I can write this one like K into magnetic field dot product along J cap, that is By. So K into J cap, how I can write it? I can write it as B1 bar minus B2 bar by mu naught into K J cap dot product with B1 bar plus B2 bar. Now when you take the dot product, it is going to be B1 square minus B2 square, it is B2 square. Okay, so when I modify it, I can get it this form, B1 square by 2 mu naught minus B2 square by 2 mu naught, which you can remember easily because this is the energy stored in unit volume. In electrostatics, we got half epsilon naught A square, which is energy stored in unit volume, right? So if I take a current carrying cylindrical shell, hollow cylinder, and current is going into on the circumference, then what will be the field inside? If I take Ampere and loop and if I do it, I will be getting field inside is 0. If I take Ampere and loop and if I calculate the field outside, it is going to be mu naught I by 2 pi r. If I take K as current per unit length, then the total current is I and total length is 2 pi r. So current per unit length is mu naught into, it is K. So magnetic field just outside is going to be mu naught into K. Now by using that logic, it is B1 square by 2 mu naught minus B2 square by 2 mu naught. So when I substitute B1 and when I substitute B2, I will be getting this result. Now we will see the same result in our regular method where K is current per unit length for this total thing. Now what I am going to do, I am going to break it. I am going to take small element and I am going to find the force on it. Now that small element looks like this, so I need to find the force on that small element because of the remaining structure. Now I have taken 2 points just inside it. I am calling it as A, just outside it is B. Just inside, what is the net magnetic field? 0. Just outside it is mu naught into K, which you can get by Ampere law. Now this small element, it will behave like an infinite sheet in the surroundings. So just beside it there is point A. So for point A as well as for point B, it will behave like an infinite sheet. For infinite sheet, what is the magnetic field? It is mu naught K by 2 and it is mu naught K by 2. But what I know, magnetic field because of this small element plus this remaining structure must give me this magnetic field, which is 0. So if magnetic field because of this element is mu naught K by 2 in this direction, magnetic field because of the remaining structure has to be mu naught K by 2 in this direction, so that they will be getting cancelled. Now similarly, magnetic field, this side is mu naught K by 2, but the total has to be mu naught into K. So the meaning is magnetic field because of this structure has to be mu naught K by 2 in this direction. So at A and at B, it is going to be, magnetic field is going to be mu naught into K by 2. So magnetic field because of this structure is going to be mu naught K by 2. So or else what I can say this element is placed in this magnetic field, which is mu naught K by 2. So I know magnetic field. So what I am going to take, I am going to take some area of it, and I can find the force on it, right? So if this length is L, if this length is small length is L, and if I take into the plane some length B, then what is going to be the area? Area is L into B, right? So or else what I can say what is the current, if the small length is L, then what is the current flowing through this small length? It is K into L, because K is the current per unit length. If K is the current per unit length, what is the current flowing through this part? It is this much into, now current I know, now I need to find what is the length of this one. Length of this one is B into I into L into magnetic field is this much. So there is a current carrying element whose length is this much placed in this much magnetic field. So what is going to be the force? Force is going to be this much. When I divide with area, sorry, this is small b, Fi L into small b. This is going to be the pressure. So when I substitute K as I by 2 pi r, I will be getting pressure as this much, which is same as this much, right? Yeah, obviously you must be getting the same answer, whichever method is easy for you. Now this question goes like, if there is an infinite solenoid, magnetic field at the center is mu naught Ni, somewhere in between. Like if there is infinite solenoid, magnetic field anywhere in between, inside the solenoid will be uniform, and magnitude wise it is mu naught into Ni. Now if you take semi-infinite solenoid, you can clearly show the magnetic field at the end, horizontal component is going to be mu naught Ni by 2, because if there is semi-infinite which is extending this direction, if there is semi-infinite which is extending this direction, if you add them, you have to get magnetic field as mu naught Ni. The meaning is magnetic field because of this one has to be mu naught Ni by 2, magnetic field because of this one has to be mu naught Ni by 2 in horizontal direction. But we can't conclude anything about vertical direction. Now you can see there has to be vertical component also. The reason is, you can see, I mean, I can prove it the other way. The other way is, if I take the total area inside the solenoid, then the magnetic field is mu naught Ni and area is pi r square. So magnetic flux is going to be mu naught Ni into pi r square. But if I calculate the magnetic flux through this one, then magnetic field is going to be mu naught Ni by 2. So area is still remaining same. So flux is going to be only half. So out of this flux, only half is passing through this. So where is the remaining half going? Remaining half must be leaking through the ends. Now the next question is, there is a current carrying wire into, and there is a current carrying loop here. So you need to find what is the torque acting on this loop because of this current carrying wire. Take this current as I0, this current as I, right? So what I am going to do is, this is the loop on which I have to find the torque. So what I am going to do is, I am going to visualize this loop like many small current carrying loops. So I am going to take one loop like this and the next loop like this. Now basically I am going to, okay, so it's like, I am going to take some loop like this, and I am going to take the next loop like this. Now if you see here, I am not there is zero current here. I am not doing anything here. So similarly, if I place one more loop here, this current is also going to be 0. So effectively I am doing nothing. I am just trying to visualize the given figure like many small loops without changing anything. I am not adding any current here. This is totally 0. So I am going to visualize this big loop as many small loops. That is not going to change any current. So I have taken some loop here at an angle theta and at a distance r. I have taken some loop. Now what is going to be that length? That length is going to be, this is r, this is going to be dr. So this length is dr and this length is going to be d theta. So this area is going to be dr times r d theta. Area is going to be dr times r d theta. Now what about the magnetic moment? Magnetic moment is going to be this direction, that is m bar is in this direction. What about magnetic field? Magnetic field, because of this current carrying wire, magnetic field is going to be tangential. Magnetic field is going to be this direction, and magnetic moment because of this loop is going to be this direction. So magnetic field is this direction, magnetic moment is into the board. Now if I want to find the torque, what I need to do? M bar cross B bar, which is going to be along this line, that is the torque because on this small element. Now if I take one more symmetrical element here, magnetic moment will be into, magnetic field will be this way. So M bar cross B bar is going to be this direction. So by symmetry I can see this torque and this torque, they must be adding up and give me only horizontal component. So what I am going to do is, I am going to find torque on this small element and take its horizontal component and integrate it. So torque on that small element is going to be magnetic moment I into that area into magnetic field there. Okay, this is mu naught I naught. Okay, anyway, I have taken small I, capital I, that you can replace in the end. So this is the torque on this small element, but what I need its horizontal component, so cos theta. So this is going to be the net torque along horizontal component for that element. Now if I want to integrate, what I can do? Here I am integrating with dr. So what I am doing is, I am integrating for all these loops so that I can get for this strip. So I am integrating from A to B for dr. Now notice this, when I am integrating for this strip, theta is going to be constant, so I can take it out of integration. So when I integrate it, I will be getting this much. Now what is this? This is the torque for this loop, for this strip along horizontal direction. Now similarly, if I want to integrate for all these such strips, I have to vary my theta from -phi to +phi. So then I will be getting this result. Now we can do the same thing by brute force method also. It is like, if there is a current carrying wire, then magnetic field here is going to be tangential. So if magnetic field is opposite to the length, then force is going to be 0. So force on this element is going to be 0. Now similarly, force on this element is also going to be 0. Now what about the force on this element? Now I am taking some small thing here, small element, small length here, and I am trying to find what is the force and torque on this element. So magnetic field is going to be this direction, small length is this direction. So L bar cross B bar, magnetic force is going to be into the plane. If magnetic force is into the plane, what about the torque about this point? Torque about this point is going to be R bar cross F bar. Magnetic force is into, so R bar cross F bar, torque is going to be this direction. Now similarly, if you take this one, magnetic field is in this direction, so L bar, magnetic field is this direction, so L bar cross B bar, force is going to be this direction. If force is going to be this direction, then the torque is R bar cross F bar, so torque is going to be this direction. Torque here is this direction, torque here is this direction. Now if you add these two torques, their resultant has to be in the horizontal direction effectively. So what I am going to do is, I am going to find the torque and take its component in the horizontal direction and integrate it. So what is going to be this torque? This torque is R bar cross force. What is the force? I into dr into magnetic field there. What is the magnetic field there? Mu naught I by 2 pi r. But what I need to take only its horizontal component. If this angle is phi, then this angle is going to be phi, this angle is going to be 90 minus phi, so its horizontal component will be sin phi. So then I have to integrate it. When I integrate it, I will be getting the required result. Now the next question. A charged particle enters a region in which there is a frictional force proportional to particle speed. the particle stops 10 centimeter from its entry from point if the particle motion repeats itself in a homogeneous magnetic field perpendicular to the plane of its trajectory. Then the particle comes to rest 6 centimeter from its entry point. How far from its entry point would the particle stop if the magnetic field is twice large? So you can see like it will be performing spiral kind of thing unstruck, right? Now first case is this one, second case is this one, third case is this one. They have given this is 10, this is 6, and they are asking what is this, right? So in the first case the only force is that frictional force, so I am calling it as minus B into V form, right? So what I am going to do is I am going to integrate both sides with respect to t. The reason is they have given V bar dt, which is displacement. They gave displacement in the first case. What is the displacement they gave? It is magnitude wise 10. So I am going to look at the magnitude. So I am going to write it this form because I know this integration magnitude is going to be 10, right? So I'll keep it like this. I have modified it this way because I will be using it further. So anyway, I got this equation. This is the first equation by using the first case. Now what is the second case? In the second case there are two forces. One is magnetic force and one is frictional force. Now I'll be doing the same thing, integrating with respect to t. Now t I can bring it here because it uses uniform magnetic field. When it is uniform magnetic field, I can say like total integration is same as integral v dt. Now this is happening only because magnetic field is uniform. Now this one I can write it this way. But what about V bar dt? V bar dt in the second case they have given as displacement. In the second case they have given as 6, magnitude wise 6. Now what about this one? This is also going to be magnitude wise 6, but I am not going to use it anyway. Now if I further write it this way, then yeah, if I divide with b, what I will be getting? I will be getting here 1 by b into f bar dt, right? And yeah, now this is going to be 10 in magnitude because what is f bar dt? F bar dt is nothing but change in momentum. Magnitude wise has to be same in all the cases. So this is f bar dt into 1 by f bar dt is going to be same in all the three cases. So f bar dt integral into 1 by v is also going to be same in all the three cases. So it is going to be 10. Right? So 1 by b into integral f bar dt is going to be same in all the three cases because integral f bar dt is nothing but change in momentum. Is same in all the three cases magnitude wise, even whatever, right? So this is going to be 1 by 10. The reason is integral f bar dt is same in all the three cases. Now what about this? This is given as 6 in the question. Now if you notice this one, this is displacement is going to be in this direction, in this plane. Magnetic field is into, so displacement cross product with magnetic field is going to be perpendicular to displacement. So this is displacement, this is perpendicular to displacement, so these two vectors are perpendicular to each other, and this magnitude is 6, this magnitude is 10, so this magnitude has to be 8 because you know that is 3:4:5 ratio, right? Right angle triangle. These two vectors are perpendicular and their resultant is 10, and one of them is 6, then the other magnitude has to be 8. You can clearly see if this value is x, then this value is going to be 8 by 6 times of x, or the ratio is 8:6, right? Now in the second question they are saying what will happen if instead of magnetic field B, if you apply 2B, instead of the same equation I will be getting, instead of B I will be getting 2B. Now I am assuming this is y. If this is y, then this would have been 8 by 6 into y, but what is the difference between this term and this term? There is a extra 2 here. So if this is y, this is going to be 8 by 6y, but this is going to be 16 by 6y. But what about this one? This is going to be same for all the three cases, so which is 1 by 10, right? So now again you can see these two are perpendicular to each other. So y and 8 by 3y are perpendicular to each other such that the resultant is 10. So from there you can get the value of y. What is y? Y is nothing but displacement in the third case, right? So you can look into the next question. The next question goes like, if there is a frictional force apart from magnetic field, then it will be performing spiral. You can see the figure looks like something like this. So they are asking what is the total distance traveled. What is the total distance traveled by the time it rotates by 2 pi radians. So time period in a magnetic field will be given by 2 pi m by qb, right? Now if you see this one, frictional force will be tangential and this will be magnetic force will be centripetal. So anyway, so you can see, yeah, if something is performing circular motion, because of magnetic field, then time period doesn't depend on the velocity, right? So even if you look at this one, like, okay, let me say this path it is following. So here it is a path of some different radius. Here it is a path of some different radius of curvature, different radius of curvature. But what I can say, the same angle rotated will take the same time. So for 2 pi radians, no matter what is the radius of circle, it must be taking same time as any circle, which is 2 pi m by qb. So that's the thing to solve the question. Time period doesn't depend on the speed, which we exploit in cyclotron also. So this is like to specify the importance of that. So then I can write along tangential, it is m dv by dt equal to minus b times of v. Friction force will be providing the required tangential. Then I can integrate and stuff. The only thing is, finally I have substituted limits like 2 pi m by qb. For one full rotation, time period is 2 pi m by qb. That's the only thing. If I substitute it, I will be getting the required answer, right? Thank you.